We need innovators who can find the answers to the problems of the future today. At eConsulate, we dream of tomorrow and make it a reality every day. Since launching in 2020, eConsulate has become Sri Lanka's hottest, multi-talented technological hub. Attracting passionate and high-caliber engineers to join our existing team of over 50 members who previously worked at Fortune 100 companies. Developing next-generation digital solutions that revolutionize the supply chain, education, disaster management, and other industries. We help companies grow by building the next big thing. When every day brings new problems to fix, we get moving. By combining agile methodology with the best practices, we can accelerate our software development to move fast and deliver high-quality results on time, every time. Our subsidiary venture, SCM Studio, provides analytical solutions and shipping management services for multinationals to streamline their import-export processes. Our innovation hub, Xavier, focuses on developing artificially intelligent autonomous robots that can safely function in hazardous environments without human operators. These robots can solve problems in construction, manufacturing and transportation industries and be deployed into disaster management situations where humans cannot go to recover wastage and save lives. Our diverse technology stack keeps us ahead of the competition, allowing our team to rotate between projects using over 20 different programming languages and cutting-edge technology depending on their interests. We train them and mentor them to compete at international levels, given our global client base. We invest in our team because we believe that they are the golden ticket to take eConsulate to new and glorious heights. eConsulate. It's where the future is happening.
Whether you are running a complex manufacturing site, powering a city's changing energy and utility needs, or maintaining a large fleet of aircraft, IFS's advanced industrial AI orchestrates data and adds capabilities to your business so you can thrive and grow. IFS.ai, award-winning asset and service management software.
So, there's this place. This place is kind of interesting.
Like me next to you, and you next to me. Hello, I got places to be. Like me next to you, and you next to me. Hello, I got places to be. Like me next to you, and you next to me, and you next to me, and you next to me, and you next to me. Hello, I got places to be.
A very good evening to all of you. It's truly exciting to kick off this second workshop of Intellihack 5 today, Deep Learning Essentials, Recurrent Neural Networks, and Convolutional Neural Networks. I'm Lakshita Sarani, and I'll be your moderator for today's session. It's so great to have you all here. For those who may be unfamiliar, the IEEE Computer Society Student Branch chapter of UCSC is a student community that empowers students to grow in tech, network with industry experts, and sharpen their skills. We let our initiatives speak for themselves, like our premier machine learning hackathon Intellihack, hosting for the 5th year this time. Intellihack is a machine learning hackathon series proudly presented by the IEEE Computer Society Student Branch chapter of UCSC. The competition provides undergraduate students in Sri Lanka to push boundaries in machine learning, tackle real-world challenges, and enhance their technical expertise. Each year, we bring top-tier mentorship, industry partnership, and groundbreaking problem statements. This year, Intellihack 5 promises to be bigger and better, with a lineup of exciting workshops, intense rounds of competition, and the opportunity to work alongside the brightest minds in AI and machine learning. Intellihack 1, 2, and 3 laid the foundation for this competition, bringing together bright minds to solve real-world problems. Last year, we hosted Intellihack Next Gen, which elevated the competition with a fresh perspective and groundbreaking innovations. And now, let's take a quick look back at Intellihack Next Gen through this recap video. A hackathon of this scale wouldn't be possible without the incredible support of our sponsors and partners. Introducing our God sponsor, eConsulate. eConsulate is a dynamic and innovative organization committed to transforming the IT sector with cutting-edge software solutions. With a passion for excellence, eConsulate strive to enhance the end-user experience while expanding their services to international clients. As our innovation partner, IFS champions technological breakthroughs and supports innovation at every level. Through our AI partnership with Standard, they are driving AI advancements and helping us shape the future of machine learning. We truly appreciate their contributions in making Intellihack 5 a success. Now let's go over the timeline of the hackathon and workshop so you can plan ahead and make the most of this journey. Competition consists of 2 main rounds. Building on that, today's session will dive deeper into deep learning, focusing on recurrent neural networks and convolutional neural networks. This session is designed to provide you with a solid foundation in deep learning, focusing on recurrent neural networks and convolutional neural networks. Feel free to ask questions at any time. You can use the meeting chat or the Padlet we've provided for discussions. It's now time to hear from our God sponsor. To introduce their company, I'd like to welcome Mr. Isuru Samaranga, Head of Global Partnerships. Mr. Isuru, the stage is yours.
Hi, everyone. I think there's a small correction on my name. I'm Isuru Samarage. I'm heading the global partnerships for eConsulate. I'll explain a bit about the company and will not take much of your learning time because that is the most important thing that is lined up for the day. I believe if I could share my screen, if the host can let me share my screen a bit. Still finding it hard, I think. screen sharing is disabled. Anyhow, I will just quickly run through about the company until we get that sorted. We are a 5-year-old company by March next month. So we have started with 2 employees back in 2020 during COVID times. We had an application in the supply chain sector, and we thought to take it global. But unfortunately, due to COVID, we couldn't travel, we couldn't actually go to places, meet clients. So we then ended up converting the company to build tech remotely for the companies around the world. So now we have expanded the team from 2 members all the way up to 220 by this month. So it has been a great journey, which I think a lot of young people, when we talk to a lot of young people, they also do have that ambition to build something. But also it is important for you to have these experiences, build real world tech, take part in events like this, and then take part in other company activities, whichever the company that you will be joining in the future. I believe that you'll have a great learning experience with whatever the sector that you're joining in, and especially you've chosen the most important, or sort of future guaranteed sort of study path when you were selecting it. But then right now, with how the tech works, there is a real question where what is the where would be our jobs in the future in IT? Will that be taken away? I get to share my screen now. And with that, I'll quickly run through like a few of the activities that we've done in the past and how we connect with the clients at the larger scale. And right now we are, as I've mentioned, we are present in 3 other countries other than Sri Lanka: Singapore, Portugal, and UAE. And these are our values and mission, which I will not spend much on. But under the company, we do have a robotics and innovation hub, which is focused on building IoT-based solutions, especially in the navigation related tech. So mainly we do have drones and robots that we are building the autonomous navigable, and also like computer vision based solutions based on them. I'll get into that a little later. This is our milestones. And under eConsulate, we do 360 product development, as well as we extend our staff to like other companies around the world to build tech. And also we do have a few other options in terms of tech, and I will slowly move into Savior and what it does. So Savior is an autonomous mapping, autonomously navigable robotic platform, which we are now creating a multi-robo communication platform as well. So this can be, this communicates with the robotics, the drone platform as well that we are building. And what it does is it can enable management of a particular company to decide, define their downtime, especially in a warehouse. And also, especially if you take like the airline industry, we do have a application now we are currently building to check the aircraft's fuselage, and then the wings from the top, especially taking the aerial view from the drone, and then taking the ground view from the ground bot. And then what we are trying to achieve there is to see what sort of defects that are there in the airplane after a routine flight. So routine flight, and also after routine maintenance check, before and after routine maintenance check. So those are the activities that we are currently doing with Savior. So which we use like a lot of lot of what you guys are going to learn during the day. So some real-time applications. And then I will not touch much about the other subsidiaries, but few products that I want to introduce to you. We do also have like a delivery platform, Uber-like platform for pick and pack services, and a multi-tenant CMS platform that we are working with like multiple clients across the world, as well as building chat agencies as something that we do for multiple clients currently. And uh, a bit from our tech stack and their framework, and also in the generative AI space, what we are doing. And also we do use a lot of AI coding tools as well to help improve the the go-to-market speed for our products. And yeah, so what we also do with partners like IEEE chapter of UCSC is to organize hackathons and startup competitions, not just in Sri Lanka, but around the world as well. So we are closely working with the Rotterdam ecosystem in Netherlands in organizing startup NL competition as a partner. That is a Netherlands National University startup competition run by Erasmus Enterprise, which will be in May this year. But it is open for global startups as well, startups and idea phase companies as well. So if you want to like check startup NL competition, you can log into NL startup competition or Erasmus Enterprise websites to get more information, and which will be at the Upstream Festival in Rotterdam, Netherlands. So you can also take part virtually for these conferences to gain more experiences as a student as well. And now this is where it becomes interesting, because we wanted to sort of share some ideas from much developed economies to Asia. Because of that, we've started a podcast called Startup Passport. I would like you to invite checking that up on LinkedIn or YouTube or Apple Podcasts. Spotify is not available in Sri Lanka for podcasts, but you can check on all the other three platforms to get some ideas of cool startups from the Rotterdam ecosystem for now. But we will be covering Japan and again few other countries in the coming months. So what our idea is to connect with the real tech builders, because we cannot now work just in isolation and not think about the real world applications of the tech we build. Why I'm telling you this is mainly to understand when we are building a robot, a ground robot, to identify the cracks and water spillages in a airline or like a runaway of a airline airport. There's another company in Rotterdam making a self-healing tar to to heal the cracks that could arise from overheating or overusage of a tarmac. So what we need to understand is tech will always especially in terms of building what we are doing right now, or like learning to be coders or learning to be building cool tech, always will have a better say when you do have an understanding of how the tech works, especially on the other side as well, especially on the physical things, IoT, and also the other industries like medical, chemical, and other real world applications. So what I want you guys to understand is to know more and know more about how medtech works, how people are working on sustainability using tech from the other parts of the world. So our idea is to share these ideas from the western part of the world to Asia, especially to Sri Lanka, and the rest of the countries as well. So go check out this. It'll be really cool for you to understand a few startups and ideas. I like the continuous continuous understanding of what happens in the world, especially on tech, but also on other industries, is very important for you to understand and land on a great idea. Yeah, that's the message that I wanted you to have. And this is a partner ecosystem, but I would bore you more with our faces more. So I'll quickly get the team to introduce you to the speaker today. We have a great speaker, and then also we thank Dr. De Silva for agreeing to be one of our knowledge partners for today. So thank you very much, guys. I hope you have a great learning experience, and I hope to meet each and every one of you if you advance through the Intellihack next phases. We'll probably get to see each other. Good luck, everyone.
Thank you, Mr. Isuru Samarage. And with that, it's my pleasure to introduce our speaker for today, Dr. Nisansu Dilushan De Silva, the Senior Lecturer at the Department of Computer Science and Engineering, University of Malta. He brings immense expertise in deep learning models, and we are honored to have him guide us through this session. Dr. Nisansu, the stage is yours.
Thank you, Kulakshi. Let me start the sharing. Hope this is visible for you now. All right. Now, I have been told that most of you are from the first year, second year, third year, from various universities. And I hope that most of you have not covered this particular topic yet, because otherwise it is going to be quite boring. Because this is going to be an introduction for RNNs and CNNs. And have it, let's say that it is a instant noodles version of it rather than full meal. So also I was told to remove all the mathematical derivations, which I have, but I do have them in the latter part of the slides, which I would not present. But if you do have questions on it, we can discuss it. All right. So all in all, we will be discussing RNNs and CNNs today. Given the way how it is organized, I'll first talk about the RNNs and then talk about the CNNs. But RNNs generally in particular domains do have better performance than CNNs. We'll see which domains which of these models work best in. All right, let us start. So first we have recurrent neural networks, RNNs. Now, in any point of time, your brain processes information as streams. You have multiple venues of these streams coming into your brain through your eyes, your skin, and all of your senses. All of these are streams. So the idea of a data stream is very natural to us. This is the thing that a RNN gets plugged into, right? So we have, if you are listening, it's a sound wave, right? They might be vocabularies, sentences, whatever I'm saying right now. You are hearing it as a stream of words, which is something that people say that it sounds like an unending stream. Anyways, then actions, right? So if it is coming out of your brain as well, it would be a sequence of commands or sequence of pulses that goes from your brain to your fingers, your biceps, and so on and so forth, right? Okay. Now, without getting into metaphysics, human thoughts have persistence, right? You do not start your thinking from scratch at each of the seconds, right? There's that joke about goldfish having only 5 seconds of memory. But even so, goldfish has memory for 5 seconds. You do not have to give the entirety of your history again each time when I say another word. Right. Now, as you read that above sentence, oh, you were listening to me, you understood each of the words. That is why I was speaking haltingly, based on your prior knowledge, right? You were partly anticipating the next word because you know how the grammar works, and you are alert of the words that came before them. So that is the basic idea of how a stream or a sequence is handled. Now, the applications of standard artificial neural networks, the proper word is MLP or multi-layer perceptrons. But generally, if you are reading something and somebody says, oh, we use neural networks, most of the time it is going to be an MLP or a multi-layer perceptron. And also convolutional neural networks, which we would get to in the latter half of this quote-unquote lecture, has limitations due to accepting limited sizes, right? And they have fixed amount of computational steps. RNNs try to handle this by not having infinite space or infinite number of computing units, but sort of simulating it by a small number of neural networks reoccurring again and again. We will see this motif of same thing being applied again and again when we are looking at CNN as well. Now, RNN philosophically is inspired by the temporal dependent and persistency of human thoughts. You will see, I am saying this stuff, but sometime down the line, I will say, okay, they don't remember. I mean, hope you do remember, we shall see. Okay, so RNNs. Many problems can be described by sequences. I will give you when you see the Riddler on the top right corner, that means I am going to ask you a question. Now I am asking you a question. Can you give me some examples other than what I said right now about you processing information as sequences? What are the real world applications that you can think of that would be handled with sequences? You can put them in the chat. These are just answers, so you can you do not have to use the other link. It is for the questions, and I don't think I have access to that. You can put in the chat or unmute and give an answer if you are there. Okay. If you are also shy to broadcast, I think given that this is a regular Zoom, you should be able to directly send me answers as a secret message as well. That is totally okay. Yes? No? Too scared? All right. here are some examples. I hope that the rest of the questions would get answered. We shall see. Okay, so examples are time series, right? Video, audio processing. These are streams. And my favorite, and even though I was introduced as a machine learning person, I am more of a natural language processing person. My work is in language processing, mostly in Sinhala and Tamil, where my introduction generally is that I teach computers, which has two meanings, right? Either I teach computers to humans or I teach computers stuff. So some of the stuff that I teach is language. So language, by the virtue of how it was created, is a string. Right? That's why we call them strings in programming languages as well. So it is a string of characters, right? Which comes as a sequence, regardless of whether it is something that when you are speaking or whether it is written down. Then when you get to bioinformatics, it's a sequence of genome. So the vocabulary is reasonably small. Generally, it is ACG. So that's small, only four of them, but still, it is a string. An infinite number of combinations, right? Every creature that you see is a collection of those small building blocks. Then process control is something, again, that can be handled with a sequence. Now, the idea here is to model this in a way that extracts the commonality, right? And sequence dependencies. What is the thing that is being repeated? What is the thing that you as a human uses? Because you might not be, some of the sentences that I'm telling you right now might not be a sentence uttered by anybody in the history of the world until now. The probability is low, but it is a possibility, right? So there's another saying that once you know the alphabet, a dictionary is just a combination of various uh, probabilities, right? Okay. Now, so what are some examples of real life sequence learning applications? So for time series, you can have something like stock prediction. It's a lucrative thing. A lot of students like to do this for their final year projects, hoping that they can spin off a company after their FYPs, right? Then we can have raw sensor data. Now, if you were actually listening to the Econsulate presentation, where they actually mentioned some of their robots and so on and so forth. So you can have various signals coming from those actuators, or voice, handwriting, and then you predict the labels or the text sequences. Then we have pure text. That is where my work is mostly. Either we give a label or a text sequence. So a label would be sentiment, part of speech. Part of speech is something like noun, verb, adjective, that sort of thing is important to tag them, right? And on the other hand, if we are doing something like end-to-end, you can have a translation, a summary, or an answer. These are the things that you do with ChatGTP or other LLMs these days, right? You give a sequence of words, right? You enter a question and you get another sequence of words. It is the answer, right? And image and video, you give a photo and get the description, which is possible. If you are in this field, if you are working on this field and you are interested and you have Googled, you might know something called clip, which is a image to caption matching data set that was created, and also the model that was trained. And then we do have a clip as well, which is called clip interrogator, where You give an image and say, if this was given to clip, what could have been the string or the caption that it would have provided. So that is how it works. Further, um, these are some examples from the nascent RNNs. You might see that these are reasonably old. That is because the basics of this domain or this subfield is reasonably old. Okay, moving on. Now, we need a method to explicitly model the order or the dependencies where we process arbitrary length examples. Because if we are, let's take the example of language processing. Various sentences in this language would have various lengths. So you can't say, okay, I'm going to take only 40, right? 40 words, right? Which is unfair of me to say you can't do, because it is something that you can do. We will see later on. And then you would do something like a buffer or a filler in order to fill up the shorter sentences, and you might process it as a batch if the sentences are longer. Those are possible, but what if we can handle arbitrary lengths, which is a good thing? Then we can do various types of mappings. One to one, one to many, right? Many to one, and many to many. I might have lied a little when I said I removed all the maths. I have some maths, but don't worry about it. Um, that is what Professor Andrew Ng says as well, right? If you have followed any of his lectures, he says, here's the math, but if you do not understand it, it's okay, right? At certain levels, right? Before getting into that, so there is the fundamental idea is that you do not need to know how to build a car to drive a car. That is generally the situation in deep learning these days. People import things and run things and they work fine, but they do not know how it works. For certain applications and also sometimes for the industry, that may be okay. But given that, I hope most of you are in this field and are not hobbyists. Not today, but by the time you graduate, I hope you would acquire the actual needed fundamentals of these foundational models so that you would be able to change them, build them, and so on and so forth, right? Someday, build something that somebody like me would come and give a lecture on, right? Okay, so getting back. The whole idea of an RNN is that it remembers something from the past. All right. So it has its old state along with the current input put in to a function to derive the new state. That is basically it. That is the difference between a regular neural network where you only have, what do you usually have? If you are looking at multi-layer perceptron and uh, other sort of neural networks, you would have seen some things like y equals sigma and some weights, right? And x and this sort of stuff, right? There is no memory here. There is only what is given at that particular point. Okay, so the difference here with the RNN is that it does have a memory of the old state, but as you may see, it is not a very deep memory. You just remember the previous thing that just happened. Okay. So we draw a RNN with this simple notation. You might see this in blogs or research papers if you read them about RNNs, right? So you have an input, you have a neural network, and then you have a state. And these loops, right? This output is to predict a vector where the YT output is from this state. Okay. Now, the way that we draw this is to spread it out like this. So if you are giving a sequence of strings like so, and putting it through the neural network in order to get a output. The next slide would be even easier to understand, right? So the easy way to understand this is to assume that we have an infinite, or maybe in some cases finite number of copies of the same neural network. And it passes a message. So every time that it fires, it calculates the state, and also it tells his son or daughter, hey, this was my state, and so on and so forth. So if we expand it further, what happens here is that we have a state, we have a function. The function takes in the state and the input in order to calculate the new state, which results in the output. And the weights of all of these is the same weight matrix, not the same values. If you are training each step, these matrix will be updated. But the idea is that there is only one single weight matrix that we maintain, even though we draw this as if it is spread out like this. Right. So if you know from your previous experience, previous lectures or whatever, how multi-layer perceptron or regular neural networks work, there are two steps. Oh, two processes, right? I'm not having much hope that people would put chats. Anyway, so there are two things that's happening, right? First, you have a forward pass. You push information through your model to get whatever the current state of the output, right? Current situation of the output. And then once you have the output, you calculate loss. And with the loss, you backpropagate it and update your weight matrix. That fundamental idea that I hope you know from your previous workshop is the same here. Now, when you do that, there is a slight issue or a slight roadblock we would face where running it entirely might be very slow. So we might, in some cases, approximate this or truncate this and only run for a little bit. And also, it will solve a different problem that we would have, which I would explain later on as well. Okay. So what are the characteristics of a RNN? It has a processing sequence of values. So xi to xto, we say, and it goes through the same network, same neural network that we have set up. And it can scale to longer sequences than by just expanding the recurrent structure, right? So you just need more copies. It's like stouts, right? And it can process variable length sequences because the block that we have does not care about the actual length of the input or output sequence. However, this is the thing that I said that I will get to. However, when you do run an RNN, if you code it in Python, you don't even have to code it. You can just import it in Python and run it. If it is a considerable, if it is a data set with considerable weight, sometimes you might run into one of two problems, which are actually opposite of each other, and you might be wondering how that happens. That happens because data sets are varied and situations are varied. The first one is the exploding gradient. Now, in neural networks, the gradient is what is most important in order to calculate the error. So it is basically the error gradient, and recalculate the weights, the new weights distribution, right? You would know this from your previous work. Now, the problem happens here, the exploding gradient, where if we are at the boundary of a cliff in the error surface, small changes might cause large error values, right? Which would cause a whole lot of changes in the weight, and it will oscillate here and there, and it might even completely diverge, right? So that is something that we call exploding gradient. So this would happen when we go from RNN. We start with the end, right? We start with the end and we go slowly one by one. And at a certain point, it might explode, as in this small change might become large and untenable. The second problem we might have is, as I said, the very opposite of this. It is the vanishing gradient. This is actually reasonably easier to understand than the previous one, right? Now, you might remember from your basic knowledge of neural networks, it has a lot of calculations with values with between 0 and 1, right? And there are rounding off errors, and there are errors with copying them into smaller places, and so on and so forth. So what happens is, if you have a plane, a flat surface, if the error is small enough, the portion of the error that gets distributed to the previous generation gets smaller and smaller and smaller. And at a certain point, at a certain depth of our long chain of RNN, it becomes negligible. And then what happens? So let's say at the very end of your neural network, you had an error of 0.1. And let's assume for some reason, this is not a very on the ground example. I'm just trying to make it easier to understand. 0.1, and the next generation or the previous iteration, we calculate it to be 0.01. 0.001, 0.00001, and so on and so forth. So at a certain point, what happens is, because you are using a certain programming language, you are using a certain level of hardware, and that gradient becomes uncalculatable. It becomes almost zero. That is vanishing gradient. So both of these problems can happen in RNNs. Now, as a solution for this problem, the vanilla solution is, before we get to that, let's say the slight error exploding and the vanishing gradient, the regular solution. So I would not get into that. The reason that I hesitated there is because I was going to go to the maths and I stopped myself. But yes, you may read the given papers if you do need more concrete information about handling this. Let's see some instead of looking at a mathematical solution, let's look at tricks. Two simple tricks that we can use if we are using an RNN to solve this problem. Right. The first one is that you can run through chunks of the sequence instead of the entirety of the sequence, right? So this is I am just invalidating something that I told you a little bit before. And I just told you you can run variable lengths, and now I am telling you no, take smaller chunks of like 10, 20, whatever, run it, fix it, run it, fix it, run it, fix it. That sometimes is a solution to our problem. This is what we call the truncated multiplication through time, because this sequence is ostensibly on time, right? Another solution is that you do not cut your string or your sequence into parts. You have the entire sequence, you run the entire thing forward, but only run the backward part to a certain depth, and then you stop. Right? So regardless of your problem is exploding or vanishing, you might have stopped before that problem happens. So that is also a solution that you can use if your RNN in your hackathon or your project is having issues. Now, if you are looking at this and thinking, oh, wait a minute, does that mean these things are not trained? Because that question, while it is okay to come to your mind, given the way that you condition yourself with multi-layer perceptions and so on and so forth, is not relevant here. Why is it not relevant here? It is not relevant here because even though we draw it this way, there is actually only one green block. This is just copies of it. We just drew for our understanding. So regardless of whether these things, this red line is here or not, does not mean anything about these blocks not getting trained, because there is only one green block and it got trained for 6 steps. That's it. All right? Okay. So the harder and more interesting solution. So these are to handle with how you present your RNN with data. But it's not really elegant. And a more elegant solution would be to have a mathematical or a theoretical foundation and change the very nature of the neural network. This is how you get published in places like Neural IPS. Huh? Now, the solution is to introduce memory for your neural network to remember what's happening. So, 2 types of cell designs were proposed and widely adopted. The first one, you might have heard of it as well, is called long short-term memory, LSTM. Do not worry about the whole mathy block here. I am not going to get to that, but I do have the slides for that. So if you do have a question, we can jump to those slides and talk about it after the main part of the lecture is done. Then a different, well, not very different, right? Look at this. It's almost the same with some little changes. Then the second one came as GRU, gated recurrent union. And now at this point, I should tell you students, I cannot tell you that GRU is better than LSTM for your problem. Right? I am not going, so that is not the question that I can ask. whether or not your problem, the thing that you are trying to do, your data set, whatever you are running right now, is going to work better with LSTM and GRU can only be found by running experiments. Right? Just because GRU came later doesn't mean that it is better. In certain cases, but even so, there are some situations. Now, let me do a counter or something that is completely opposite to what I am supposed to do here. I am supposed to teach deep learning and neural networks and so on and so forth. But in certain situations, right, and even certain research applications in certain configurations of data, sometimes things like SVM and random forest work better than multi-layer perceptrons in certain types of classifications. You can see them in black and white if you look at certain types of research papers working on this type of data. So newer does not always mean better. And just because you have a problem and you have a framework that can import a deep neural network with multiple layers and complex um, configurations does not mean that you have to use it for your problem. In fact, if the complexity of the model that you are trying to use is higher than of your problem, what happens? Again, I am not allowed to use mathematics, but it would learn something we would call the identity function inside of it. And the excess of the model complexity, whatever, let's say it's the weight matrix, would carry garbage weights, right? And you would have a hard time training your model, right? It will always be undertrained. So, like it was a small side comment. Just because something is new doesn't mean that the new thing is the thing that you use. And just because something is complex doesn't mean the complex one is the thing that you have to use. Okay, keep that in mind. Okay, coming back. Now, both of them process information in an additive way, where the information is flowed from the older state and the current input to the new state, which is shared, right? Sent forward. And the sigmoid gates are used here, and it gives between 0 and 1. I think you already know the sigmoid function, hopefully, from when you were looking at basic neural networks. So whatever the weights and the biases that you have, this is basically what happens. Again, I am not going to go to step-by-step slides. Okay, now, these architectures helps with the vanishing and exploding gradient. Why? Because now it remembers not just the state, but some of the information that came from the previous inputs. Right? Previously, we were only passing the state, but now you do remember the input as well. And now I am going to ask questions. Hopefully, this time you are going to answer. Again, because just like the previous time I said, okay, you could have answered that question if you were paying attention to the consulate presentations. Here, you should be able to answer this question if you were paying attention to the first few slides of this lecture, right? Now, can you give me some examples of one-to-one one to many to one, many to many situations that are shown here for various types of real world neural networks. No? Too afraid to answer or too sleepy? What's happened? No? Let's give one answer. One would be a standard neural network model. I cheated here, right? It's the pointless answer. I'm giving you the pointless answer. The pointless answer is something like a multi-layer perceptron. You have an image, you classify it. Any answer for the second one? No? No one? Oh, good. One to many. Image to caption. Very good. Very good answer. Take an image and output a sentence or words. That is exactly the example that I wanted to show. Okay, next one. There are two configurations of many to many, you can see. One where, so what is the difference between these two? The difference is in this configuration, you take the input sequence completely in, and then only after that sequence is over, you start to generate the outputs. Here, you have the inputs, and immediately when you are seeing the inputs, you are generating the outputs, right? Even though both of these are many to many, that is the difference. So many to one as well, I was waiting. No. So a sequence to input would, so many to one would be something like a sentiment analysis. You have a sentence or you have a review of a movie and you need to classify it as a positive review or a negative review. Then it would be a many to one situation where you can use an RNN, right? Number 4 is an example of machine translation. You wait until the end of the sentence to translate to the other language. There is a good real world joke slash situation where a German ambassador or a representative at United Nations was making a very angry statement, and people were looking at the translators who give the live translation, and the translator said, "I am still waiting for the verb." Because in different languages, the subject verb object order is different. And in certain languages, you can't start the sentence. You can start the sentence and finish it with the verb. And in other languages, you need the verb in the middle in order to say the right. So, good example. I don't know how many of you in the participants list speak Sinhala. But a good example is I go home to Mama Gedara Yanama. Right? In fact, let's take it from Sinhala to English. Mama Gedara Yanama to I go home. Until I say Yanama, you can't go to the second word in I go. Right? So Mama can be matched to, okay, Mama, I, immediately translated. Gedara, you can't do anything in the English sentence because the object in English is at the end. And only after I say Yanama, then you can say the English word going or go home. So that's the example there. And sequence of input and output, an example is video classification, labeling, object tracking, that sort of things. Okay, let's move on. Now, I really, really hope you would answer this question, new question. Can you see now everything that I said? RNN is good. We can settle. We can solve sequences. We can handle language. I was bragging about RNN all the time. But can RNN handle all types of sentences or language? Can you see a problem in these two sentences that they are not complete sentences, but can you see a problem happening if I am going to use an RNN to process whatever the sentences that these things are going to build? I would go to the bank to the board. If an RNN was given these sentences and it was processing word by word, and as it is processing word by word, it was giving you predictions or whatever, could these have caused a problem? And what is the problem? Any answer? No? Okay. So the first sentence, it can say, I would go to the bank to catch some fish. Right? In that case, I am using the word bank in reference to the river bank. Or I can say, I would go to the bank to deposit money. Now, until you see the latter part of this sentence, you would not be able to know the type of the word of bank, right? Actually, the semantic meaning, the meaning of the word bank is not apparent until you get to the latter part of the sentence. Now, the board decided to go ahead with the merger. Then I am talking about a board of a company. Or if I can say something like the board is attached to the legs of the table, then I'm talking about the board of a table. This problem or this quality of language, we call it polysemy. Right? A single string has multiple meanings. It happens in all languages. Another problem, more interesting problem even, is something that we call a garden path sentence. Now, I am not going to read out these next two sentences for the simple reason, if I read them out, the problem goes away. Okay, so I'm going to be silent and show you two sentences and read them yourself in your mind, and you will see the problem. These are grammatical sentences, and when you read them, when you start to read them, at a certain point, you stop, confused, go to the end, read it again, and then you understand. So, if you read something like the old man, then confused. The boat. But then you understand the word man can have different meanings. And here it means the old, comma, man the boat. Old people would handle the boat. That is what that sentence means. Next one. The complex houses married. What? What does that mean? And single soldiers and their families. This means the complex, as in like an apartment complex. Houses doesn't mean the houses, but given those houses. The apartment complex gives accommodation to married and single soldiers and their families. See, these are called garden path sentences, but as you can see, the meaning of the man and the word houses could only be understood by getting to the end of the sentence. Now, how would we handle this kind of a thing with the RNN? For that, we use something called bidirectional RNN, right? Bi RNN. No, BR in whatever that you like to pronounce it when you are doing a presentation. Right? Anyway, it is bidirectional RNN, or in brackets you will have something like BI-RNN, where you run it both ways and create uh, um, the context or the state. So in certain scenarios, in most of the models or frameworks that you use, you can directly import a bidirectional RNN. But again, remember what I said earlier. Just because it is a complex, just because you have access to a complex model or a complex architecture, does not mean that you should import it for all of your problems, right? Make sure that you are using Occam's razor and selecting what is best suited for your situation. Sequence to sequence model. This was actually, so this I gave an example earlier as well. So you have input sequence and then you have an output sequence. This was, you will see this SCQ to SCQ all over the place. Developed by Google in 2018, and their objective was to use this for machine translation. It uses RNNs and like different types of RNN. You can look at the example on if you are using PyTorch. They have a nice demo. And in fact, the link that I would send the organizers is actually me going through that demo and showing you how to do the coding. Um, so they do have a nice demo on creating a basic translator out of this. Now, this scenario, this configuration we call encoder and decoder. So we have an RNN as an encoder, and then we have an encoded semantics, encoded idea, or we call it context, and that context is passed to the decoder. Right. So if you are in your problem, if you are using encoder decoder architecture, know that it originated here. Why we would like to use these things, especially it is very useful for things like machine translation. So if you are translating regular, if you want to take underlying semantics, I love you to Jutama. And if there are different word orders, as I was giving at the previous example, so in English, it is I eat a red apple, but in French, it would be je mange un pomme rouge, where pomme is apple and rouge is red. The way that the language works, the adjective comes later. So this, okay. So again, that is a little bit of a lie because, well, it does work. It can work with this, but in order to perfectly use it, you need something called attention, which I don't have time to get into. But you can get mediocre results with just RNN, but with RNN with attention, you can get reasonably good results. Okay, with that, we end RNN. Right? So RNN has GRUs and LSTMs with RNNs with memory, and they have broad applications. You can even, if your problem is small enough, if your problem is small and the data set is tiny enough, you can even use vanilla RNN to solve it. You do not need an LSTM or a GRE. But if it is complex and it needs the memory, you can use one of those and try. So that is the RNN summary. Here are the RNN references. So next I am going to move on to CNNs. But before I move on to CNNs, if you have any burning questions, you can put them here. Yes? No? Do you have them? No. I don't see any. Okay. That would have been useful. Okay. Let us move on to CNNs. Now, as I said, technically, CNNs should have been before RNN, but I took a conscious choice to do CNN after RNN for the simple reason that even though I was instructed to remove the maths, CNN is very mathy, and if I remove all of the math from CNN, it becomes nothing. So for RNN, it was a little easier to remove the math parts, but for CNN, we'll have to touch a little bit at least on the math, right? To understand, it should be reasonable, right? And also CNN might not be state of the art in certain places, but learning it helps you understand the others, right? Okay. Now, everything that I said about RNN, right? So I said that it can be used for various things, and among them was language. And then I sneakily told you that this one of the biggest discoveries in RNN sequence to sequence was by Google, and they were doing what? They were doing translation, right? And if you do go away and read yourself, and I also gave a little bit of a spoiler for attention, and that also came for the problem of translation, right? In fact, the very problem that I showed you earlier about word ordering and what word is important to create what to generate what other word in the other language. That is why attention came into being, and then it begot the only attention model where they pull out the attention and thought, can we just only use attention? And thus, there was a paper called Attention is All You Need, which created transformers, not the cartoon kind, but then it ended up with all the other types of transformers, and that T in GPT is transformers, right? Right. Now, the reason that I told you all of those is to tell you that even though RNNs may be used in all of these other areas, its home is language processing, right? Its home is language processing, and then everybody else adapted it, right? It can be used for image processing, video processing, stock price prediction, all of those. So that is how things work in computer science, right? Somebody invents something, and then it can get adapted to other stuff, right? While we are not going to talk about it in greater detail, a very good example on deep neural networks being reused is we are not going to touch the fundamental or principle that is used. It is called transfer learning. Again, something that you can read if you like. Would example not very recently, about few years ago, is that in Japan, uh, a pastry shop needed to automatically calculate their bills, right? So think about something like bread dough, right? You go and put your stuff on your plate, and then you go to the give me 1 second. Then you go to the counter, and the person at the counter looks at all of those and gives you what you are due. Well, they wanted to automate it, so they have a camera and they take a photo of your plate and gets calculates your the price. So they trained a neural network for this, and it was working well. But then they realized the same neural network that was used to identify donuts and croissants can also be used with a little bit of training to identify cancer cells in your dietary tract. Why? Because the cells are reasonably similar in shape to donuts and stuff, right? So in not just in deep learning or machine learning, in computer science as a whole lot of things that were invented for one thing later on gets used for other stuff. Now, I came to that point from RNNs being in language and being used for others. Now, the reason that it was important at this point is that CNN was invented for image processing. But then we are using it for various other stuff as well. You will see how. But you need to understand the entirety of the way of thinking in CNN is based on the fact that images are matrices, are a square or a rectangle, right? Okay. So with that, what does a computer see? A computer doesn't see as you see. A computer sees blue, green, red, not like this, like this. It sees a matrix of numbers. And it might be something like this. This is from the MNIST dataset, which is a very popular handwritten character dataset. Now, what a computer sees is RGB of a picture that you have, and it does not. So the RGB channels can be separated like this. But just because we separate it, it is only for our benefit that I have put them in these colors. But what it sees is actually a grayscale of each of those channels, right? And those are several matrices. And a pixel is one of these. Okay. Now, let's try to handle this with a regular neural net. When I say regular neural net, I mean a multi-layer perceptron. So we had a 28 by 28 matrix of number 6. And we are going to handle this with a regular or a multi-layer perceptron. How are we going to handle this? Because there's going to be a singular layer of neurons. We stack this one after another, which means we are getting 784 times 1 of a single line. And then we try to use 100 points here to reduce it and calculate the weight count, right? So what's happening here? We have a weight matrix of 100 times 784. That is a whole lot of parameters. Let's add the bias as well. That's a whole lot of parameters. Just to understand a 20 by 28 by 28 image. Lot of them. I don't even want to calculate it. This is only just a single channel. And then you add 3 colors. Right? Whole lot of numbers to calculate. Thousands of values. So, and also, the orientation of this number 6 is destroyed. Because we sliced it one by one and stack it on one another. The whole point of this being close to this is completely destroyed if we try to make it a sequence. And it is not invariant to transformation. So what does that mean? If I move the 6 to the left or the right, or up or down, or turn it, the whole thing, what it is getting, is going to change. Okay, let's not talk about the rotation. Let's talk about only translation. Translation doesn't mean language translation here. It just means moving this 6 to the left or the right or the top or the bottom. It is not invariant. It becomes completely different if we move it. Now, if we use a sparse set of connections, right? We all the weights having the same color shared. If we have a way where we only process these, then we would have less number or fewer number of calculations to do. If we are only processing some and we are sharing the weights. But remember that the motif is shared, motif is the same here previously and here. There is in order to make the calculations better, we do some weight sharing. Okay. So here what we use is called a kernel. So here, not the military kind, but the food kind actually. So what we do here is called a single degree of convolution. Okay. Don't be scared, but what we do here is just take an input vector and put it through a convolutional kernel and getting a answer. So the star operator is generally in mathematically called the cross correlation operator, but in computer science we just call it convolution. It will help you with an example, right? So let's say we have the input vector of this and the kernel of this. And what really you are doing is multiplying this pointwise. 1 times 1 is 1. 4 times 2 is 8. You're not even answering those, right? This is 0, this is 0. So 1 plus 8 gives you 9. That's it basically. And the output size in a 1D convolution is W, capital W minus simple W plus 1. So when you push this kernel to the next position to get this number and so on and so forth, you will get the output of this size. As you can see, what is this? It's a compression operation. You are losing some of the information, but you are getting the gist of it. It's like you are squeezing a orange. So what does it do? If you have an input image like this and your convolution kernel looks like this, you would get a convoluted image like this. As you can see, it's a smaller or a more compressed representation of what you had earlier. So if you have an image of a mouse like this, and you run this kernel, you would get that information saved, right? So you had this line over here, which had a certain thickness, and that's why we have various values here, right? So this is a value of 50, this is a value of 20. Why? Because this might be black and this might be a little gray here. And here it is another level of gray. But once you have once you run the convolution, it would once you run the convolution with the filter, you would get a smaller value. Right. So it would identify uh, the patterns that we would expect it to identify. Okay. So the key idea is we have an input image. We need a convoluted image. We need to learn what is the matrix that is needed to multiply. Basically, that's it. So the derivation of it is assume this is a input feature map. This C, take it as the number of colors, right? So if it is RGB, that is, we are using images as an example. That's always it is going to be the same thing, right? So 3 channels are there, the width of the image, the height of the image, and you will have a kernel that is going to be processed, that is going to be used on this image. This gray block shows it being applied to this top corner. And once you apply it, you will get a smaller output which corresponds to this, right? So I'm not going to go to the math. I'm just going to show you it as things that happens, right? Okay. Again, don't worry about this. Don't worry about it. It is applying it and you are getting the size W minus W plus 1 size. Okay, let's see. Step by step. Let's do this. You have a 32 by 32 and 3 channel image, and you have a filter of 553. Let's try to apply this. Now, 3 is the full depth or the number of channels that we have. So, each of those blocks will get mapped to a single number. All right? That is why we are going to get a smaller thing, right? So now we had a 32 by 32 and 3 image, and we have a 553 filter, which would mean we get 28 by 28 by 1. Now you might be asking, why? Why did you get 28? How did you calculate that value? We'll get to that slightly, right? So we can do this with one filter, another green filter, another red filter, yellow filter. What these colors does not mean the color of the image. It just means different types of convolutional filters, and after which you might be able to get a number of different activation maps. So these things might be extracting different qualities, different types of features of the original matrix. As I said, initially, someone has enabled transcription. Let me say okay to it. Initially, this came from image processing, right? Image processing people have had things like processors, filters long time ago. They had things like Sobel filter. I will get to that. I just show it, but not get into that. Long time ago to do things like edge detection. So they brought that thinking pattern in order to model this, right? So people working on language thinking, I have a sequence and I need the sequence after it. I am translating. Okay, I listen to the sentence and I am going to do a sequence. Those people invented RNNs. People thinking of images, I need to find edges on this side and that side. They created CNNs. So you can't remove the invention from the inventor, right? The thinking pattern is embedded into the end product or the neural network that was created. So think of it. If you are going to invent a neural network someday, whatever the problem that you are solving, that might come into play. Right? It's not just an architecture; it is a neural network itself, right? A type of neural network. So basically, the computational graph of this is very simple. What you are having is a input, you flatten it, then mathematical multiplication, and you reshape it, and you get the answer. So notice that this is slide 47 and this is slide 52. That is not a mistake that I have made. That is the fact that all the math slides, I hid them, right? Okay. So as I was saying, uh, uh, the convolutions, the types of convolution that you use are actually do have a longer history. They have been used long time ago in image processing, right? Even many Photoshop effects would have those convolutions, right? So if you use uh, convolution or transition vector, sorry, transition matrix, where the whole point is that this little corner is missing and everything is shifted to the right and the bottom, and you run it on this matrix, this image matrix, you will get a moved image, which is a translated image. Again, translation here means moving. Similarly, if you use a Gaussian filter, so Gaussian is Gaussian in the 2D space is this. You know this, right? You have seen this. This is how your Z score was calculated, right? Okay, let me rid of this. So if you use a Gaussian, this is a 2D Gaussian, it blurs the image. If you have a filter like this, it will emboss it with the direction of the embossing going this way, right? Why? Because it is organized in -2, -1, and +2, +1, this way. So you can see it from the embossment and the shadows that is under the embossing. Okay. Now, that is what people use to, let's say, to come up with convolutions. But now let's see how the convolution, once you have a convolution kernel, how we are going to do it. Here I have to define another word which is called a stride. The stride is the same meaning as you have as a human. Stride is the distance that you go by steps, right? The size of the step for the convolutional operation. So let's say here's a convolution with stride 1. You have a 7x7 matrix and a 3x3 filter, let's say, and you move it by 1, by 1, by 1, by 1, right? So if it is a 7x7 matrix and you are looking at a 3x3 filter, you are going to get, okay, let's see whether you can answer this. What should be the size of the output you think you are going to get if I use it, if I use this here? You just saw that for a 7x7 matrix input and a 3x3 filter, it took me 5 steps to go from left edge to the right edge. How many, or what is the size of the output image or the convoluted image you think? No answer? It would be 5 by 5 because every green block will generate one value. So 5 steps there, and again 5 levels on horizontally as well. So you will get a 5 by 5 output. What if we are using stride 2? First stride, second stride, third stride, over 7 by 7 input, 3 by 3 filter, stride 2, you are going to get 3 by 3 output. Oh, this looks good. Let's do 3. But no, you can't do it. Why? Because it wouldn't fit. As soon as, so the second one, the second step will be here, right? 3 by 3. Then you can't have one here. Stuff is outside. Okay. So that means when you are actually using CNNs and you are coding and you want to set these sizes, you have to be careful when you are setting the strides and those you are setting those variables. But generally, you students, you don't care. You just copy paste it from some blog, and the calculations are already done. But if you are actually doing it using your brain and trying to customize it, you need to know how this works. So how you calculate the size of the output that is expected, because if you do not do this properly, if you do not give these numbers properly, because these are going to be layers going on to other layers as well, right? So that is how you get, I don't know whether how much of coding experience you have, but this is how you get size mismatch errors, right? Saying blah blah size of matrix cannot be passed into blah blah size of matrix, or shape error depending on the things that you are using, right? So okay, output size is actually determined by n minus f divided by stride plus 1. So if it is n is 7 and the f is, the filter size is 3 and the stride is 1, you get 5 by 5. Remember, we looked at this example. If it is 2, you get 3 by 3. If it is 3, you get a non-integer answer. That is why it doesn't work. Okay? Right. Now, at this point, can you tell me, again, I don't have much hope because you guys are not answering or putting anything in the chat. Does this seem unfair? Now, each of these pixels, if you think of these pixels as people, do you think all of these pixels are treated equally so far? Do you think, do you see some pixels that are treated unfairly? Yes. So one person says no. That means some of these pixels are treated unfairly. What pixels are treated unfairly so far? Which of these pixels? The corner ones. Very good. So corner ones and edge ones are, especially corner ones, are very unfairly treated, right? So this pixel only gets considered once, and this pixel only gets considered twice, this thrice, and this 4 times. No, this is also thrice, again thrice, twice, once, twice, thrice, 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 twice, once, right? So we have to solve this unfairness, because otherwise your image that you are processing will not extract information if they are in the edges or corners, right? So all of those will get unfairly treated. So how do we solve this? We solve this by adding padding. So again, when you are using your own neural network, let's say you are using PyTorch, you will, and you are setting up CNN, you will have to use padding. Why we are using padding is to solve that problem. We add some filler around our original matrix, right? Generally zeros. Zeros are the general idea. So that the pixels that are unfairly treated now are going to be the padded pixels, the fake pixels that we added. The the corner pixel, the original corner pixel will have the same representation as the middle pixels now because of padding. That is the whole idea of why we add padding. And then the width or the size of padding is dependent on your size of the image and the size of the filter that you are using, mostly size of the filter, right? There you are. Now, let's say, now we have a input of 7 by 7. We have a 3 by 3 filter with stride 1, and we have padded now with the 1 pixel border. What do you think is the size of the output? Any idea? No? What you should do is, the equation doesn't care. Equation doesn't care whether it was an original pixel or a padded pixel. Now what we have is, what is the width of the new image? Is it 7? No. Is it 8? No. It is 9 because you have padded around, right? So it is 9 minus 3 divided by 1 plus 1. So 9 minus 3 is 6. 6 divided by 1 is 6. 6 plus 1 is 7. The size of the new reduced image is going to be what? 7 by 7, which is actually good. So we have made sure that our corner pixels are handled, and also we have made sure sort of that it is not deteriorated. But sometimes we do need it to corner in or to funnel in for various reasons, which I don't have time to touch. Things like if you are using an autoencoder for removing noise, that sort of thing. So we do need sometimes to funnel it and then bring it out. Okay, but right now we are at a position we can take a 7 by 7 image and create a more compressed, but again a 7 by 7 image with the information squeezed in. Okay. Now, convolution sizes, to summarize, we accept a volume. We need hyperparameters like the number of filters, the spatial parameter, the size f, the stride s, and the amount of zero padding p, and it produces WH2D2, where the W2 is, as I said earlier, remember W1, the size, minus f. Now we have 2p. Why? Padding goes both ways. Okay, that is the default, but nobody stops you from only padding one side. But obviously, that means that non-padded edge would be treated unfairly. Grant would be very unhappy. Similarly, H2, same equation, and D2 is going to be K. If it is symmetrical with an height computed equally by symmetry. Okay. So with parameter sharing, right, those weights would be the same, right? And in the output volume, the deep slice has, we get the deep slice by operating the convolution on the deep filter, using the deep filter on the input volume. So this is an example. Generally, we use K as a power of 2, right? 32, 64, 128, 512. When you are filling it up in your, let's say, PyTorch, you will keep that in mind. Okay. Now, there is a concept that I want to tell you about. It is called equivariance. It is, if you are familiar with the Marvel characters, you would know that it means it's the same thing, but not the same thing, right? So a function, it's equivariant. F is equivariant to G is if the operated on X on G operated on F is equal to G operated on F. So parameter sharing can cause the layer to be equivariant to translation. That means moving, right? Any function that translates the input is equivariant to G. So here it is, we see how we can use to move. However, convolution is not equivariant to other operations which scales or rotates. Okay, so now that was a very fast part of one of the two this thing, the one of the two parts of CNNs. Now you might be thinking, oh my God, only one part is covered. What about the other one? Other one is very easy. It won't take that much time. It is called pooling. So pooling is where you take a bunch of numbers. It is a compression operation again. What it does, it takes a bunch of numbers and gives you a summary. So when you are creating a CNN, you would see it has layers, convolution layers, pooling layers, convolution layers, convolution. It doesn't matter. Well, it matters, but ultimately, what happens in a pooling layer is getting a summary, and the type of the summary can change, right? So what happens here? You have a tensor and you get a smaller tensor. So I'm not going to get to the mathematics of it, but let's get to the idea of what happens here, right? You have a 224 image, and this operation we call pooling in neural networks, but image domain, they call it downsampling. So there are multiple types of pooling, but the most popular ones are max pooling and average pooling, which is a very easy thing to know. This is the only thing max pooling does is take the red square. If it is a 2x2 filter of pooling, it just puts the max. 1156, max is 6. 2478, 8. 3212, 3. 10344. That's all. This is max pooling. It's not a big deal. It's a big word, but this is all it does. What is the max of the box that I am right now looking at? That's all. Okay. So we can look at the invariance here as well. Now, let's put them together. We have layer patterns. So now the building blocks of a CNN are these two things. And there can be others like dropouts and so on and so forth. But generally these two things. You have CNN layers, you have conv layers, convolution layers, you have pooling layers. And then you can have linear active ReLUs or whatever, fully connected layers, FC, that sort of things. Right? Then the art of it comes from you knowing how to arrange them in a good order to solve your problem. The concept of CNNs is the same, but the invention comes on how you arrange them. Right? So you can have multiple convolution layers, linear rectifications, pooling, max pooling, average pooling, and again convolution, and so on and so forth. Right? Doesn't matter. Now, here is an example. You have convolution and ReLUs, pooling, convolution ReLU, pooling, and then fully connected, and then there's a classification layer, softmax. And why do you use softmax? I don't know whether you know that. If you are doing a multi-class classification, you do a softmax, right? So here is a generalized CNN architecture. You have an input, you have a con and ReLU n times, whatever the n times. Then maybe you have an optional pool m times. This can be replicated, and then you get to a fully connected layer and a ReLU layer k times, and then there is a fully connected layer, which is generally something like either if it is a single output, it is going to go to a single thing, and or you can go to something like a softmax. So you decide what the variation, what is your CNN is. So this is something that you would have to experiment and find out when you are solving your own problems, right? You would have to tinker with it and find out. So all of these that I am showing here are valid CNN architectures. The first one, you can't, it is unfair to call it a CNN, but it is the minimum solution where NMK is 0, which is basically a linear classifier, right? And then the second one is a multi-layer perceptron, right? So there's this thing in mathematics, complex things can be compressed or reduced to smaller previously solved problems. So that is what is happening there. But from the third one onwards, it is actually CNN. Okay. So as I said, the art of it, the talent of it is there in the way that you organize these layers or manage these convolutional and pooling layers, right? So there are multiple people who invented various, like these configurations, right? Lanet in 1998, right? I'm not going to like go into a lot of details, but they solved handwritten zip code numbers, right? And then AlexNet, you might hear about this. VGG, still used for image classification. There are papers come out even right now about we use VGG to classify this image data set. You can even import it in good what do you call good frameworks with deep neural networks, right? Another one that is still used, ResNet. Well, not this version. ResNet came. ResNet has various other versions as well, right? So what they just added? You can see how complex the neural network is. But fundamentally, what they have is a singular loop, feed forward loop, and a weight layer, ReLU weight layer. That is basically it. That is the building block of ResNet. So you can see that. So all of these, like for some problems, ResNet might be better. For some problem, VGG might be better, and these are still used. So all they did is come up with a configuration by themselves to solve the problem at hand. So you also may be able to do that with the unique configuration for your problem. Okay. So the idea of CNN, again, unlike the issues that we discussed in RNN, generally CNN deeper is better, but that does not mean CNN is free from the curses of vanishing gradient and stuff. They are still there, and you need to solve them if you are doing something like that. That is why actually they had to do things like forward passing, forward bypassing, that sort of stuff. So practical tricks. What can we do? We can take pre-trained models. If you have, like, what do you know? You have 1,000 examples, 1,000 images. You need to classify. Can you train these very deep models? No, you can't. What you do is you take a pre-trained model and fine tune it. Right? You take something like ImageNet. The ImageNet currently knows how to classify. So you are thinking, oh, I need to classify what books and newspapers, let's say. Can you do it? Yes. You take ImageNet, which is currently classifying cars and dogs and cats, and fine tune it to your problem. Why can we do this? So this is, as I said, I will just mention it, not talk about it. Transfer learning. Transfer learning is a neural network that has been trained for something else. We take it, that knowledge is inside it, and then we fine tune it for our problem. The reason that this is possible is because the fundamentals of this problem is the same. So if the system knows how to classify cars and dogs, but the virtue of it being possible to classify cars and dogs, it already knows how to process an image and recognize segments and so on and so forth. So that can be the same where you are trying to classify newspapers and books, because the fundamentals, the basic parts are the same. So how does pre-trained models work? You have a pre-trained model, you take it, you classify, it does the classification, the feature extraction part is the same, right? Okay. Now a question. CNNs. Okay. I will get to that question. CNNs for natural language processing. How now? Oh, everything that I said, all image based, all needs a matrix. How does it handle language? Didn't I say language is a sequence of words? It's a flat line, right? Remember the bad example that I gave in the very beginning? A single line, 1D convolution. I said that it is bad for this thing. It destroys connections and so on and so forth. So how are we going to use CNNs for natural language processing? How did they solve it? How do you think? No? What they did is, for each word, you get an embedding. Embedding is a vector. And then they stack the vectors on top of another. And when you stack a number of vectors on top of another, what do you get? You get a matrix. That's the solution. Right? How you do NLP on CNN is you have stacked. Oh, let's use the pointer. You have stacked the word vectors and have gotten a matrix. Okay. So before going to the next point, another person is asking, can you tell about the YOLO algorithm? It is a CNN 2 years and how it differs. It's a paper by itself. YOLO is a very successful image classification, image segmentation, object detection algorithm. You can take it out of the box and use it. And there was YOLO 3. So again, it is not my domain. So if I remember correctly, YOLO 3 is the newest one, which is very good. It's pre-trained. It is CNN, and what it does is, it once you give an image, it will draw the bounding box and do the classification. Right. So you can put an image of cars and say, okay, tag like of a road and tag me all the cars. It tags them, and if you use their classification model as well, it will say it is a car or a van. not 100% correct, but still it's good, right? So if you want to do something like detect objects on your in one of your pictures, that is how it does, right? In face recognition, there were all the things like Haar classifier and that sort of thing, but and if you are going to build a system to recognize sign language, YOLO can be useful, right? You recognize, you can go to the level of individual fingers, and or you can recognize the points where the fingers are moving, right? And get the skeleton or the stick figure of those to get an idea. So you don't need you do not need YOLO. YOLO is not basically YOLO is not the only thing that it can do that can do that thing, right? So there are things like open pose, which also can take the locations of people, like from from their limbs and so on and so forth, or detect things on your face, like around the mouth, where the nose is, and around the eyes to do face masks and so on and so forth. So yes, this field is quite interesting, and there's a whole lot of people and a whole lot of different algorithms in this domain. There is no point in like as in like I can I gave you like one of your friends asked me about YOLO, so I told her about YOLO, and then I gave you an example of open pose as well. But obviously, there might be more. While we were talking today, while this lecture was happening, maybe somebody else invented something as well. That is how this this domain works. It moves very fast, right? New things come out every day, right? Especially if you are looking at generative image generation, that sort of things. SD models come out every day, right? Even like 2 days ago, some new realistic trained model got released. Okay, now some insight. Why uh, the backward thing works is because the fundamental parts are common. Edge detection, segmentation, those things that we used to do manually automatically happens. But you can see it by having a CNN and experimenting or looking at its middle layers, and that is what has happened here. These things do not make much sense to you, but these are actually edges that were detected. And here, like little ghosts, you can see maybe a tire getting detected, right? Maybe a side of a door getting detected. So when you go layer by layer, it detects more and more complex parts of this image, right? You can see the pattern on in the front of this car being detected here, right? That sort of a thing. So this is why this transfer learning is possible. We can this low level feature, mid level feature, maybe that is the same for a car and a dog, right? An edge is an edge. A circle is a circle. So those parts we can keep from that billions of images trained by Microsoft or somebody. And then we only unlock these later layers and train them for our application, utilizing whatever they have done previously. So that is basically uh, uh, how you use pre-trained models. Okay. So let's see. So here are the CNN references. I think we had time as well, slightly more. And do you have any other questions? MC, do you want to take it?
Yeah, sure.
Okay. All right. Again, I don't see any questions from my end other than the ones that I answered as I was going. Uh, if you send some to the other place, this form thing, I do not know. Organizers, do you see any questions that in the form that you have sent? No. Right. Uh, then let us end my part here. I think again, MC, please take over.
Okay. That was an incredible, insightful session. A heartfelt thank you to Dr. Nisansa Dirushanti Silva for sharing his expertise and valuable insights with us today. Your time, knowledge, and passion for the field truly made a difference, and we deeply appreciate your generosity in guiding us through this learning experience. To officially conclude today's session, I'd like to welcome Ms. Anuja Sekar, Manager of Talent Acquisition, to share a few final words. Ms. Anuja, the stage is yours.
Hello everyone. Can you guys hear me?
Yeah.
Okay. So thank you so much for inviting me for this session. So I'm Anuja, like working at eConsulate. So I'm heading the talent acquisition team, right? So let me also discuss a few points. I think since you guys majority wise you guys are into second year, third year, so probably you guys are looking out, and then again you also see like what are the things that you can also improve in terms of get selected from employers, or maybe get a good offers, right? So if you talk about in the industry level, it can be any industry, but mainly if you're talking about IT software industry, most of the employers, they are expecting few key points from the candidate, right? So there are so many, like if you take technical skills, if you take soft skills, there are so many, expectation nowadays the employers are having because of the evolving of the technology and the IT trends. But let me also talk about the five main points which are very much important for y'all to improve in terms of, get more selection from any companies you wish to apply. So one is the communication skill. So we do a lot of interviews, we take a lot of interns and all, but also like if you can present yourself well, if you can, communicate properly, okay, these are the projects I have done in my university. These are the team work, I have done. These are my thesis, or these are my research. If you can talk about that, or else you can also showcase these are the coding part I have done. Something like that, if you can clearly communicate to the interviewer, because usually it's a technical round, so if you can do that, that will be more good. And the time management. Now, I think if you all are starting off with your project, if you all are starting a career, and if you have the good career path, so each and every time you have this deployment, you might have to, face your client. So time management is something really expecting from the employer. Being a fresher graduate, it will be more helpful if you can also, practice throughout your university as well. And the third point is leadership. Now, you guys doing a lot of events. I think this is one of a great event we have, start off now. So I think this will have more time. So you can also, have the collaboration and, participate for this event, the competition. So likewise, if you can make it a point where you also have a very good, leadership quality, whereas you support each other. Likewise, that will be like something very important. And also the other point is problem solving. Now, if you take about, this hackathon and all, so you might have a lot of problems. So then if you can also find a way, okay, I can support this, or you can, being a teamwork, So likewise, if you can also improve your problem solving skill, that will be really good. And also ability to, make it your work bit more faster. Now, if you can improve that with your time management, also, learning quickly. So that is also one of the key expectation, whereas the employer is expecting from anyone who is willing to apply. So these are the few points that I would like to discuss in terms of the soft skill, whereas the employer is expecting. And the second point I wanted to talk about it now, I see a lot of CVs, lot of resumes, lot of application coming to eConsulate as well. And the key few areas which you can also improve in terms of making a CV, that will be really good. So I will also share one sample profile as well at the end. So if you can make it maximum 2 page, that will be really good, because a lot of profiles are coming in. Because so as a recruiters, TA, as an employer, like we actually expect people to reduce, like every details including in the CV, because if you can make it 2 pages, that will be really enough. And also talk about what you have done in terms of your project details, in terms of your experience, what sort of skills you have. So that is, if you can include it, that will be really great. And also few points nowadays, like everywhere you go, you heard this ATS friendly application tracking system is everywhere. I think we also like practicing that. So if you can make it clear view of what you're currently doing, about your skills, and about your experience as a summary, if you can make it. And also you don't have to really need your profile picture. You can because the ATS systems or anything, that it won't be like capturing that. So because of that, if you can add that also, like without a picture also, that is fine, right? And also you can make it like a bold letters. What are the things that you are really capable, right? Keywords, you can bold it. And you can also mention the references, the projects, and also if you can make those sort of things, then I think the CV looks very clear. And also, like when once you go to an interview, make some time, just to brief yourself to the employers. So because of that, you don't have to include all the details in CV. So just make sure that you are updating a proper method of CV, check the grammars. I think sometimes those are very simple mistakes the candidate making. And also the key point is, you have to make sure that updating what is the position that you're applying. So as bold, or you can maybe make another font, or you can make a a 12 or 13 size also fine. Just make a great bold letters. Just make your what you're looking for, what is the position. So likewise, if you can clearly mention, and also just mention the objective or your career summary. Likewise, if you can mention, it will be look very nice. And also you have some more time when you go for an interview also, you can present yourself. So let me just show one CV. I think that will be helpful for you. Hope you guys can see my screen. Can someone confirm if you can see my screen?
Yeah, we can see.
Okay. So here this is something we just I just wanted to showcase. So this is one CV, right? So you can see just a few pages, and you can like make it a very simple bold letter. So that will be really helpful. Now, I'm not taking too much time. So I know you guys, already here for a long time. So then now everyone, like to apply your interested companies, right? And also like few of you like to apply consulate, right? So if you wanted to apply to our company, obviously like any company, if you go, you can also understand what are the products that they are doing, what sort of company, what sort of culture they have, what sort of a work life balance, whether the company is giving. So for that, before I concluding about e-consulate, I also would like to showcase some. So these are some of the activities, engagement stuff which we are doing. So we celebrate at e-consulate the festivals, and also every month, end of the month, we also celebrate few things, where to keep the employees engaged. Because like Monday to Friday, like daily they are working, especially the engineers, they might have to, work late nights if there's any deadlines and all. But then also work-life balance is something very crucial. So work-life balance itself, how we are working, how we are balancing your work. That is something very crucial to understand. So these some of the engagement stuff. So if you can do that, then obviously employees also have some sort of a break and flexibility, and they can also refresh their mind to do better more job. And also we never forget to award, like giving rewards to employee for their exceptional hard work and dedication he is doing, right? And then again, see, this is our CEO, Mr. Subodh Pereira. So this some of the things that I can showcase, like if you do like your job continuously, if you are learning fast, if you also have some sort of a career, what sort of a thing that you wanted to do and all. So if you achieve certain things like the milestone, definitely as a company we also like spotlight. So we call it as spotlight honors. So we also give that as well. And then again, if you see here, so these are some of the year-end parties we have done, right? Interpretation saying that okay, you can also participate, showcase your talent. So these are some of our team members, whereas they are doing some activities. So they will be also like not only working. Definitely, you have the work-life balance, and also you will participate. You will grow. You can think about that as well. And so I think that's the majority part. I think Mr. Isuru has covered about the e-consulate products and everything as well. So now talking about e-consulate, so this is our page. If you have any more questions, you can reach out through e-consulate page as well. And you can see our, job post we have uploading, I think weekly, that is done by Ms. Nirdusha also. So you can reach out to her, you can reach out to, or you can, any queries, you can put it to e-consulate information. And also you can just, this is my profile, Sekar Anuja, you can reach out to me in case that we can help you on that. So with that, please don't forget to follow our page econsulate.net, and you can also drop your CVs or any queries like how to make a CV, or is there any interview techniques that if you all are interested to ask, or any sort of you can reach out to us. And any question that anybody have, please feel free to ask and I can clarify. So we have few minutes. Yes, hope it's clear for you all. Okay. Okay, I think yes, thank you so much for that question. I think yes, you can apply for internships. Currently, we do have few openings as well. So definitely you can apply. So we can check on that. If your profile is very good, then we can go ahead with an interview. So technical round is also there. And yeah, if you get selected, we are happy to onboard you as well. Okay, so thank you very much. Yes, Ms. Kulakshi, you can take over. Thank you.
Heartful thank you to Ms. Anuja Sekar. With that, we conclude today's session. Thank you all for being part of this workshop. A quick reminder, there are more exciting workshops coming up, so be sure to stay tuned and gear up to compete in the Premier Machine Learning Hackathon Intellihack 5. Good night, everyone.